Let me begin with a word of prayer. Heavenly Father, we thank you for this day. And we pray for the Calculus 2 students that they would recover and come back stronger tomorrow. And I just pray you help us use this review time wisely, Lord. In your name I pray. Amen. So at the end of the video, I sort of proved something. And that was Cayley's theorem, right? And what was Cayley's theorem? What does Cayley's theorem say? It says this. If you've got a group and the order of G is equal to n, then there exists G bar, which is a subgroup of S, symmetric group of order n, such that G is isomorphic to G bar. I mean, this is Cayley's theorem. In words, it says that any group of finite order can be basically seen as a subgroup of the symmetric group of nth order. And not just that, in a kind of natural way. See, because the proof of this was what? A proof sketch, let me remind you, because the proof sketch actually will explain why I do what I do in the examples I'm about to show you. The proof sketch was essentially this. Given G and G, right, you can define L sub G from G to G how? L sub G of x is equal to Gx, right? This is left multiplication by G, as we called it. I have trouble spelling multiplying class. Multiplication by G. All right. And notice that LG inverse LG of x is what? LG inverse of Gx, which is G inverse Gx, which is x, right? And likewise, we've got that LG composed with LG inverse is equal to the identity on G. So what that shows to you is that, well, I mean, to summarize, LG inverse is equal to LG inverse. Best seen and not heard for the usual reasons. And that's good for arbitrary G, right? So every left multiplication operator has a, an inverse. And also if you have two of these things, right? If we took LA, LB, you can prove that it's LAB, like that, right? Because if I take LAB of x, it's LA of bx, which is ABX, which is LAB of x, but x is arbitrary. So what this shows you is so the inverse function of any left multiplication is another left multiplication. The product of two left multiplications is, again, a left multiplication, right? And, of course, left multiplication by the identity is what? That's just the identity on G, right? I mean, so my point is that the left multiplication maps, if you look at the set of all these guys, right, that's a subgroup of the permutations on G, right? Oh, yeah. Well, it's debatable. Right? Not really. How can I abbreviate? There's not much abbreviating to do here. I just have to face the music. Yeah, you got me. It's not a good sign, really. Not a good sign at all for the remainder of this review session, not even remotely. It's very bad. Very bad indeed. But I think I've given you evidence that the set of left multiplication maps has identity, is closed under inverse, and is closed under composition of functions, right? the composite of two left multiplication maps again. So this gives us that this set of left multiplication maps is a subgroup of the permutations of G, right? It's a set of bijections, set of mappings from G to G, which, right? And so by the subgroup test, this is a group, and it's not too hard to prove that the left multiplication maps are isomorphic, right? So if I call this thing, you know, G bar bar, then it's fairly clear that G bar bar is isomorphic to G. How so? The isomorphism is kind of dumb. It's just psi of G is equal to LG. You can prove that that's an isomorphism from G to G bar bar. The reason I'm calling it G bar bar is G bar is something else still, right? G bar is as a subset of the permutations on the first n symbols, right? So that's something a little bit different. So what would that be? So if we let G equal to, say, G1, G2, Gn, like that, then to get from, oh, how can I say that? I don't even, how can I say this? You want to trade, let's say, trade F in, so suppose F in G bar bar as F of Gi equal to Gj, okay? So it's a, you know, G bar bar is a set of maps from G to G, right? So it takes an element of G and maps to another element of G. What would the corresponding, and we want to trade this for, let's say, phi of F, an element of G bar, which I'm saying is a subset, is going to be a subgroup of Sn. How's phi bar of phi bar? Excuse me, phi of F. This is going to be a permutation. This is going to be a mapping from n sub n to n sub n again, right? Because it's a permutation. It's one of these Sn's. So like if I take phi bar of F and I let that act on I, it should just give me back J. So in this way, I trade a permutation on G for a corresponding permutation on 1 through n by just supposing that it sorts the labels the same way it sorts the group elements corresponding to those labels. This is way easier to illustrate with an example that, I mean, like, I think it starts to get kind of hard to understand at this point with all my bars and bar bars and so forth. Let me show you an example specifically. Let's see here. So we know C3 is what? 1a squared, right? So if we look at left multiplication maps on C3, what are they? I need to come up with a less annoying name for this. Let's call it, I don't know, you had a homework question which actually was about these things, remember? I think it was called NM. So in the spirit of that monoid homework problem, end C3. So it's got the identity map, right? It's got left multiplication by A, right? And what else does it have? Left multiplication by A squared, right? This would be what I was calling in the generic proof G bar bar. Okay, so here's the idea. This is like the first thing. This is like the second thing. This is like the third thing, right? So if I start with 1, right, and I left multiplication, if I do LA on it, what does it take me to? 1 left multiplies to A, right? Left multiply again. A squared, right? Left multiply again. We're back where we started, right? because a cubed is 1. So in other words, we're taking 1, we're mapping to the second group element, then to the third group element, and then back to 1 again. So LA corresponds under this mapping I'm describing, sideways TIE fighter phi, it corresponds to the cycle 1, 2, 3 in S3. And likewise, you can get LA, what happens if you look at LA squared? 1 LA squared, we go to A squared, right? LA squared acts again, we get A to the 4th, which is equal to A, right? And then let LA squared do its magic again, you're back where you started. So this cycle starts with the first thing in the group, it goes to the third thing in the group, and then it goes to the second thing in the group with my labeling. So LA squared is, under the isomorphism described, this is isomorph. This transfers to the element 3, 2, 1. And then, of course, there's the identity map, which is just the identity permutation corresponding to the identity permutation under the isomorphism. And so, in summary, this G bar is the identity permutation, 1, 2, 3, right? And 3, 2, 1. There you go. This is a subgroup of S3, which is isomorphic to the cyclic group of order 3. I want to make sure I work an example that has more than sort of, this has 2 cycles in it, right? But they're kind of the same cycle in the sense that they involve the same group elements. I think it's good to look at another example, at least one more example, and then I'll take your questions. Another example I thought would be helpful with this one. I thought this is a nice group to look at. It's pretty small, but it's got some nice structure, Z2 cross Z2, right? So let's say that that's 0, 0, 1, 0, 0, 1, 1, 1. My ordering, by no means sacrosanct. But let's say that, I pick an ordering. This is the first thing, this is the second thing, this is the third thing, this is the fourth thing in the group, right? So my left multiplication operators, what are they? We've got L0, 0, which is equal to the identity, right? That's really annoying to write. It's too late, I wrote it. We have L of 1, 0, right? And so the way that works, that is equal to 1, 0 plus x. In this left multiplication, quote unquote, is left addition because we're in an additive group. What happens when you do L of 1, 0, L of 1, 0? We get twice 1, 0 plus x, like that, In other words, we get x again. So in fact, left multiplication by 1, 0, 0, 1, and 1, 1, they're all like this. These are all, if you operate on them, they all just give you back the identity if you operate twice, They're their own inverses. Okay, so what should we be looking for Cayley's theorem if we want to illustrate Cayley's theorem here? To illustrate Cayley's theorem, we're looking for what? G bar, right? A subgroup of S4, because this is a group of order 4, right? So let's see here. If I start with 0, 0, these pictures are very boring, and then I let left addition by 1, 0 work on it, what do I get? Right? And then, oh, I'm sorry, I shouldn't do for, yes I should, I'm sorry. Stop, idiot. Me, not you. And then, well, back. right? I mean, it's very boring. So that's a transposition for the corresponding subgroup, right? You're going from 1 to 2. So this one, and then likewise for, let me just stick a fork in it here. So G bar is going to be the identity permutation 1, 2, 1, 3, and then 1, 4. That's the isomorphic subgroup of S4 to Z2 cross Z2, also known as the Klein 4 group, right? 3 elements of order 2 in the identity. Also isomorphic to what? Group of units of Z8, right? This same subgroup of S4 would illustrate the Cayley's theorem for Z8. Like this would, for Z8, this would correspond to 3, perhaps. This would correspond to 5. This would correspond to 7. This would correspond to 1. Group of units Z mod 8, right? That's another version of this group that's isomorphic. It's the Klein 4 group. So to do that homework problem that I gave you, what you need to think about is the left multiplications for the quaternion 8 group, and what do, right? Like what do they take, what are the sort of closed cycles there? For example, I'll just tell you one of them, I. You start with I, multiply by I. I mean, we'll start with 1, multiply by I. 1 goes to I, multiply by I again, go to minus 1, multiply by I again, go to minus I, multiply by I again, minus I squared, which is 1 again. So the quaternion 8 group apparently has 4 cycles in it. This is not surprising, right? It's an isomorphic version of the group. If your group has elements of order 4, the isomorphic group from Cayley's theorem must also have elements of 4. How do you get elements of order 4 from permutations? You can use a 4 cycle, or you could have 2. Nope. You need a 4 cycle. We could have least common multiple of, if we have a disjoint cycle composition, it's the least common multiple of the cycle lengths, right? So I was about to go least common multiple of 2 and 2 is 4, but that seems kind of like spelling left with a T first. It's not good. All right, I got this out of my system. You guys ask away. By the way, I'm happy in here. If you'd just like to remind me of all the various times in lecture I've said, gee, that'd make a good question for the test. If you'd like me to work through those things, if you happen to have a laundry list of them, I would be happy to systematically like attack those for you in here, unless you have other questions. But that was one thought I had. I could do that if I can find an eraser. That is, no, not a good eraser. But see, this is just going to make it worse. I know already. Well, yeah, that was wrong. Yay. Sometimes it's good to be wrong. Any questions about this? Okay. It's kind of funny, like, I don't know. I'm not sure Cayley's theorem is really useful. It's like, yeah, it's something you can do, but it's kind of like saying you can take something and rewrite it as a matrix multiplication. I mean, it's useful, but it's also not terribly restricting either. I mean, there are some nice, I mean, we do know how to manipulate permutations. We know a few things about them, so it does get you something, but one of the things it means is that, whatever you could say about permutation groups, right? It's probably something, if you can say something about arbitrary permutation groups, it's probably something you can say about arbitrary groups of finite order, because an arbitrary group of finite order can be put inside one of these permutation groups, right? Yeah? Don't all speak at once.
I guess, could you prove the theorem that you showed us the other day? I guess it would be a good test proof. It's the inner automorphism.
Oh, yes, 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 that would be a good one. So the statement was in G was a subgroup of aught G was a subgroup of the permutations on G, right? All right, so let's start with in G. Maybe I should start with aught G, actually. So aught G is what? This is sigma from G to G, right? Such that two things. Number one, sigma is an element of the permutations on G, which is to say, that's just a snazzy way of saying what? AKA sigma is a what? Sigma is a mapping, well, sigma is a bijection, right? That's what that means. A permutation is a bijection on the set. So that's number one. Number two, it means that sigma of xy is equal to sigma of x, sigma of y for all x and y in G. So an automorphism is a homomorphism. In fact, an automorphism is an isomorphism from the group to itself, preserving the structure of the group. Okay? So as I'm thinking about why is aught G a subgroup of the permutations of G, right? That's the question we're trying to answer. Point number one, essentially by definition, aught G is a subset of the permutations of G, right? Because that's part of the definition of automorphisms, is that they're at least bijections, right? Number two, if we look at the identity map on G, right? And we feed that x times y, what does it give us? It gives us xy, by definition of identity map, which is also what? The identity on gx, the identity on gy, right? By definition, identity map. So therefore, the identity map on G is an element of aught G, right? So I'm looking to use the subgroup test. I don't know it's finite, so I need to check all three. Well, 4. It's a subset. It's got the identity in it. What else do we need to check? Right, so let's, we'll check closed first, right? So if alpha and beta are elements of aught G, then we can look at, what is this automorphisms of G is what kind of group? It's a subgroup of the permutation group, which means we're talking about composition as being the group operation of the automorphism group, right? So we'll let x and y be elements of G. Then we look at alpha, beta of xy, right? This is alpha of beta of xy, y. Definition of function composition. I'm going to stop writing that sort of thing. But if I asked, I would be happy if you wrote that, if I asked you to prove it, obviously, you know. Okay, then what? Well, beta is a homomorphism, right? So beta of x, beta of y. Beta is homomorphism. And then that is alpha of beta of x, alpha of beta of y, as alpha is homomorphism, right? But then by the definition of, what's this? Alpha beta of x, right? Alpha beta of y, you know? So what does this show us? Let me just emphasize here. This implies then that alpha beta is a homomorphism, right? That's a homomorphism. But what else do we know? The composition of bijections by chapter 0, right, is a bijection. So alpha beta is a bijective homomorphism. Consequently, alpha beta is an automorphism. And then inverses, right? We need to check inverses. See, how's that go? Alpha inverse exists, right? We know that because it's bijection. So we should look at alpha inverse of xy. And let's see here. Let's call that, let's give it a name. Let's call this thing z. Because I can't think of anything else at the moment. And then if I take alpha of z on both sides, what do I got? I got alpha of alpha inverse. You guys might see a better way to do this. I probably will once I'm done with this, but this is what I'm doing at the moment, just to show you how I get out of a corner when I get in one. So sometimes, usually after I write this down, I'll think of a cleaner argument, but you know, it's one of my methods. xy is alpha of z, right? I'm not sure that's really helping. Oh, you know what I should do? Should be sneakier is what I should do. I sometimes get hung up on this particular part of the argument. Let's see here. How about this? This is well, the question is why, we're trying to figure out why is this equal to alpha inverse of x, right? Alpha inverse of y. I mean, that's what we're trying to show, right? How about this? Since x, since alpha is onto, right, there exists a and b in G such that what? X equals to alpha of A, and y is equal to alpha of B, right? So alpha inverse of xy is actually alpha inverse of alpha of A, alpha of B. Now I have a platform to use the homomorphism property for alpha, which is assumed, right? Because now I can say, aha, well that's alpha inverse of alpha AB, right? Which by definition of inverse, that's just AB again, right? Which is what? Notice that we also have what from this? This tells me, among other things, A is alpha inverse of x, and B is alpha inverse of y, right? So this is alpha inverse of x, alpha inverse of y, which shows you then what we wanted, namely that the inverse of a automorphism is once more a homomorphism, but it's also a bijection, so it's again an automorphism. So automorphisms are closed under composition and inversion. The identity's in there. It's a subset. By the subgroup test, we have this one, right? Questions? I don't know. Like sometimes I get hung up on the inverse step for certain groups. It's harder for me to come up with an example where closure gets me trouble. Like I don't usually have trouble with closure personally. I don't know why. Just to me that's more natural, like 3, but 4. Sometimes the inverse is just sneaky. I don't think that's the case for the next one though. in G is what? This is a little bit more sort of formulaic. This is sigma sub G from G to G, such that sigma G of x is equal to gx G inverse for all x. So these are the conjugation maps. Conjugations are particular kinds of automorphisms. I guess that's the first thing, is that actually an automorphism, right? So let's see here. So we should actually explain, our first order of business is to explain why it is that NG is a subset of aught G, right? That's not immediately clear, right? If I say you multiply by G and G inverse, it's obviously an homomorphism. I don't think that's obvious. Is it a bijection? I don't think that's obvious either, right? I mean, we need to prove those things. The easiest way to prove something's a bijection is to just exhibit the inverse. What do you guys think the inverse of sigma G is? That would be nice, right? Let's check if it's right. So sigma G inverse of x would be what? By definition, right? But the inverse of the inverse is the thing again. Which is, hooray. And it's fairly clear that the other composition goes just the same, right? So well, I mean by symmetry, the argument, sigma G inverse, sigma G is equal to the identity on G, which is equal to sigma G inverse, which we actually showed. Therefore, every conjugation map is, in fact, a bijection. So at this point, we have earned the right to say that the so-called inner automorphisms are a subset of permutations of G. This shows that they're a subset of permutations because each one's a bijection. It remains to show that they're actually homomorphisms, right? So now we should show that, you know, if we pick sigma G, right, an element of NG, is it a homomorphism? Is that true? What do we need to check? X, Y, right? So check this. This is a fun one. So G, X, Y, G inverse. So you guys, you tell me what to do. How do I mean, I'm trying to get to sigma of G of X, sigma G of Y. So like, what should I, what's my next move? I'll do it for you. G, X, E, Y, G inverse. I'm supposing E is equal to the identity in G, okay? I know Nicholson uses 1 a lot of times. I was raised to call it E. You go either way, I don't care. It's fine. Just don't call 1 0. We'll be okay. For some reason, it doesn't bother me if you say E for 0, but it really bothers me if you put 1 for 0. Anyway. I can trade this E for what? G inverse G. We have a winner. That's a year. And the reason that you should do that is then, by definition of the definition of sigma sub G, that's what we have here. Which then, since X and Y are arbitrary, shows that sigma sub G, in other words, conjugation by G, is a homomorphism. And it's a bijection, right? Because we just showed it has an inverse. So it's 1 to 1 and onto. Consequently, every conjugation map is also an automorphism. Now this alone does not show, so you notice all we've done at this point, right? What have we shown? We've just shown sigma g is an element of aught g, right? So in other words, we've shown that ng is a subset of aught g, but that's all we've done. What remains to do in order to show that ng is actually a subgroup of aught g? What's left to do? I've made these homework problems in past years. You see why? They're actually pretty good homework problems. Maybe I made them a homework problem of yours. I forgot. It's totally possible. That's very real. I don't remember so many things. To show it's a subgroup, we need to check subgroup test. Is the identity in there? Is it closed? Is there inverses? But now we're asking those questions for ng, right? So how do you can notice that conjugation by the identity is the identity on G, right? So identity is a conjugation by the identity is the identity map on G. Point number 1. Point number 2, if we look at sigma G, sigma H of X, what do we get? Let's just work it out. That is what? That's sigma G of HX, H inverse, which is GHX, H inverse, G inverse. Sock shoes for the win. GHX, GH inverse, right? So that, guys, is sigma, that's conjugation by GH of X, right? X being arbitrary, we've shown that this identity holds for the map. The mappings, rather. So this shows you that sigma G, sigma H is in fact equal to sigma GH for all G and H. Well, it's more to the point, for all inner automorphisms, for all sigma, this is sigma H, sigma G, sigma H in G, you know? One thing's left. What else do we need to show? We need subgroup test. We need to check that it's the inverse, right? Oh, but we already discovered that earlier. We already showed that it's closed under inverses, right? We found a formula for the inverse, but we also proved that conjugation by the inverse is the inverse of the conjugation. So 4, we already know 4 from earlier arguments. So as inverses given by. So we get that the inner automorphisms of G are in fact a subgroup of the automorphisms of G. There you go. In fact, I don't think we assumed anywhere here that G was finite, did we? If you look at these proofs that we've just done, nowhere do we assume finiteness, right? So this is good for finite or infinite groups. Now, what actually becomes trickier is to actually find all of the inner or outer. But outer, what's an outer outer automorphism? Those are the inner ones. What are the outer automorphisms? If the terminology makes sense, what would you guess? Surely an automorphism that's an outer automorphism. Surely an outer automorphism should be a automorphism, right? And if it's outside, it shouldn't be inside, right? So the outer automorphisms are the automorphisms which are not conjugations. So you can just look at conjugation by group elements. Those produce all the inner automorphisms, and then whatever else is out there, those are outer automorphisms. actually figuring out what those are for a given group, I don't know if we quite have the technology to really understand it yet until we have the right homework problems and discussion. That hasn't happened yet, I don't think. I don't think it's a reasonable test question. I don't believe it's yet a reasonable test question to ask you to calculate the inner or outer automorphisms for a group. On the other hand, any of the things we just did are like decent but challenging questions. And a drag for me to grade unless I give a lot of guidance, right? Because I'm like, which part are they doing? Because there's a lot of parts. But anyway. Goodness gracious, that took me forever.
I was going to say, that's a really long test question.
Yeah, well, it's easier for you to write than it is for me to write. And yeah. What else did I say would be a good test question? Do you guys even remember?
Says that, like, if you have it on two automorphisms, then G is affiliated by H, but you also says.
Ah, yeah, that one's right. Weren't those proofs pleasant? I thought those proofs were pleasant as they go. What is it? Is this from the mission or from?
No, it's another theorem that you said you didn't really test.
Okay.
It's, wait, just a second, I wrote somewhere as above. I don't know what it is.
If you tell me a little bit of it, I'll probably remember it.
I don't know, it's from a while ago,
Oh.
like way back.
Oh no. I hope this isn't some cyclic group thing.
This is the one. I'm not sure, you might have already.
Oh, this one.
And
Yeah.
I think above might be that.
Yeah, that one won't take long. Sure. Yeah. So the other, what she's asking about is when I suppose we have like, I know I got to come up with a notation. I need some kind of notation for the operation. Let's say I'll do pound sign sub I. Haha, I know what you're thinking, but you're wrong. No. So this groups, all right, for I equals to 1, 2, n. And then what I said was that we can make G1 Cartesian product G2, Cartesian product Gn. Let's call that whole thing G is group with operation star given by x1, x2, xn star y1, y2, yn is equal to, so this is the definition of this product, okay? X1 pound sign 1, y1, comma, x2 pound sign 2, y2, and so forth and so on. So the point is we operate each component according to the group operation of that component, right? And the theorem that, let's see here, the theorem that Mackenzie's reminding me about I claimed that the inverse of a tuple was the tuple of the inverses, right? So this isn't really a theorem, this is a definition, isn't it? Sorry. Let me fix that. There we go. So this is the definition of the direct product of G1 through Gn. So the theorem that I claimed was, if we look at x1, x2, xn inverse, it's just equal to x1 inverse, x2 inverse, xn inverse, right? So where, of course, each one of those inverses refers to the inversion inside that particular group, the component inversions, which I will not invent yet another notation for, if you don't mind. I mean, Nicholson has the good sense to just use juxtaposition for all of these operations in the book, right? That's wise. So, look, and and I guess the other thing we also needed, and the identity, right, in G is E1, E2, en. I mean, we might as well prove that while we're at this, because without that we can't do, I mean, we need to know the identity before we can prove something about the inverse carefully. So first of all, let's just look at EG times x, right? So that's EG times x1, stink. E1, E2, en, x1, x2, xn. I'm just calling x the tuple of x's just to have a short notation for it, if you don't mind. So ex is that, but by definition, this is what? And then what are these? Because that's the identity in G1, that's just x1, right? Because that's the identity in G2, that's just x2. Because that's the identity in En, that's just xn again, right? And of course, we can also write that as, you know, x1 pound 1 E1, x2 pound 2 E2, xn pound n En, which by definition of the operation is x1 xn star E1 en, which of course is x star EG. You see, I've committed 2 cardinal sins of my notation so far. I will fix them now in red. Star. Star. So what does this calculation show you? In summary, we have that EG star x is equal to x star EG for all x in G, right? Which suffices to prove that the tuple of the identities is in fact the identity for tuples, right? It's the identity for these vectors of group elements. So much writing, not so much thinking though, right? Now, the calculation for inverses is really almost the same thing. So if I take, you know, x times x1 inverse, x2 inverse, xn inverse, that's, I'm assuming x1, x2 xn. I forgot my stars again. Goodness gracious. Star. So this star, now you see why I didn't do it in class? It's x1 inverse because it's easy, but it is tedious. So to make this more fun for me to grade on a test, a simple thing I can do is set n equals to 2. I find out if you guys understand without burdening myself with so much to read. Now this is, of course, x1, pound 1, x1 inverse, x2, pound 2, x2 inverse, xn, pound n, xn inverse. You notice that my proof is lacking commenting at the moment, and that's bad. I mean, I should really, I'm not going to, though. I'm tired, guys. I can't write down more. Let's see here. So that is E1, E2, En, right? So if I name this thing, if I say that this is x inverse, you can see that x star x inverse is equal to EG, right? Is also going to be equal to x inverse star x for all x in G, which is to show that the tuple of inverse is the inverse of the tuple for arbitrary tuples. The proof that G is a group, I mean, this is part of it. This shows identity, this shows inverses, but the proofs of closure and associativity are very, very similar, right? Closure, just take two arbitrary things, multiply them. Every component is the multiple of things from that group, which is, again, a thing from that group because these are groups. So by closure of the components, we get closure of the tuples. And then by associativity, well, associativity was the same thing. Again, it's because when we multiply, we can associate component-wise because every component's a group. And but to actually write it down, it would take me 5 or 10 minutes of, yeah. But I hope you understand what I'm getting at, because it is a very important and nice way of constructing new groups for old groups, right? For example, if I want a group that has elements of order 2 and order 3 but is not cyclic, wait a minute. Oh, shnikes. I was about to say this would not be cyclic, but why would I be wrong? You had a homework problem, right? In your homework problem, you proved that if you take cyclic groups of relatively prime order, that their Cartesian product is again a cyclic group. So, oh well, that won't do it. But anyway.
For this test, is last year's first test like a good guide?
Probably not. No. I just deny. I haven't looked at it, so I don't know.
Okay.
I'm just going to say no. Because I'm pretty sure the structure is a little bit different this year in terms of where we get to for the first test. See, because that video I had you guys watch, I was berating them for using multiple notations in their definition of group. So that shows me that I had not covered isomorphism before test 1. Being that I've covered isomorphism, and you noticed how excited I got talking about isomorphism, you kind of know there's going to be some isomorphism questions on the test, right? They can't be super deep because we don't have that much to work with yet, but I don't know if they ever get super deep in here, honestly. But so surely cyclic groups, what's a monoid? Is this function well defined? The things we've talked about. No, we haven't talked about those so much lately. I mean, we've talked about other things, but that table problem is always interesting. So I asked that last year's test 1. I might ask that again. What's that? No, here's elements, list the order of elements in a table.
Oh.
Did I do that on the test?
It's in our homework.
Because if I did that on a test, it'd be super useful for your homework, huh? That seems like a wise thing to do, right? Look at last year's test before you finish this year's homework. You might save yourself some effort. I'm not saying that's absolute, because the thing is, I remember last year making the test, and what I'll sometimes remember is the process of making it, right? Which I usually make a test which is about twice as long as what I give you guys, and then chop, 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 chop. So sometimes I forget the difference between reality of what I gave the test class versus what I wanted to give the hypothetical class, all right? And so there's that. So it could just be I was thinking about putting that table on the test. It didn't actually make it. That's my point. Well, guys, it's been fun.